Thank you, Dr. Roberts. Do want to thank you all for your time and for your attendance today. And as was already mentioned, we'll have a time period for question and answers at the conclusion of the presentation. But I will try to keep this to within a reasonable time limit. So my dissertation research was on the design and operation of electrochemical solid oxide cell systems for spacecraft applications. And I'm doing this research under the Propulsion, Power, and Thermal Systems Lab here at Tennessee Tech University, which is directed by Dr. Rory Roberts. What is the research motivation here? Just as a review of the problem, spacecraft, the mass and their volume confinements make it a challenge, and sometimes it's infeasible to bring on board all of the components that maybe a designer, mission designer would so desire. And in addition to this, the electrical power that is oftentimes supplied by batteries, again, constrain operations to zones that are lit by the sun, have a high solar irradiance if you're going to work off of solar panels. So we want to ask the question, what about space missions that have a longer duration and they're at a much further distance away from Earth orbit, where the solar irradiance begins to fall off logarithmically? So, and what about satellites that have no solar panels whatsoever? What kind of missions would that open up if we could get rid of the solar panels altogether? On the right-hand side, you see here a table of some of the modern systems that are on board a satellite. And again, as we look here at the propulsion, if you are thinking about including an ion thruster in a satellite, you're looking to do any kind of emergency maneuvering, or again, thrust impulses of a long duration. We need to look for some kind of power source that has a higher specific energy than the one supplied by current electrochemical batteries. Just as a point of reference, many payloads are taken up to orbit now on board the SpaceX Falcon 9. It has a maximum payload volume of 145 cubic meters and 145,000 liters, and a maximum payload mass to low Earth orbit of 22,000 kilograms. A lot of times we hear about price per kilogram to orbit, but one point that I will put forward as being relevant is also thinking about the volume constraint. Oftentimes we just think about the mass constraint, but the volume constraint is just as important for many satellite and spacecraft designers. So this is the research motivation. Now, as we think about developing power on board a spacecraft using a fuel cell, specifically here a solid oxide fuel cell, we want to review the advantage that fuel cells have over batteries. So using a fuel cell, we can establish an electrical power plant by tapping into existing fuel and oxidizer supplies that would already be in place for a bipropellant thruster-equipped spacecraft. As well, chemical energy storage in the form of propellants does not suffer self-discharge in the same way that batteries do. And you can think about your cell phone, which will go from 15% charge to 3% charge in just a few minutes. As well, this also decouples the redesign of an electrical power plant for a given spacecraft or satellite. It decouples that redesign process from the standardization of current propellant tanks that are already being used. And an effort like this to tap into bipropellant supplies could benefit from recent on-orbit servicing efforts. So The Northrop Grumman company actually sent up another satellite, the MEV-1, that docked, serviced, and boosted an Intelsat 901 back in February of 2020. The Intelsat 901 was running low on fuel supplies, so it sent up this additional craft to boost its orbit. So that might open up possibilities of on-orbit refueling as well. Now, why are we interested in solid oxide electrochemical cells? Well, SOFCs that would be used are resistant to the poisoning that oftentimes takes place in lower temperature fuel cells, and they do not need the precious catalytic metals like platinum to the same degree as lower temperature fuel cells. Also, SOFCs are fuel flexible. Again, this opens up the opportunity of interfacing with existing bipropellant pairs. A brief history of fuel cell usage on board spacecraft. Back with the U.S., the Gemini missions, General Electric developed an alkaline fuel cell. This was followed up by Pratt & Whitney's effort to develop an alkaline fuel cell for the Apollo program. Now, for the Apollo program, 3 fuel cell stacks were created, operating at about 28 volts. And they developed 1.5 kilowatts for the Apollo command and service modules. The specific weight of that system was 90 kilograms per kilowatt. The space shuttle also used alkaline fuel cells for a 12 kilowatt power system. There you can see the increase in onboard electrical power from the Apollo program to the space shuttle program, and future spacecraft are going to need even more electrical power. After the development of the alkaline fuel cell, NASA did have plans in place to replace the space shuttle fuel cell with a PIN cell. Now, pertaining just to the use of solid oxide electrochemical cells in space, solid oxide electrolysis of carbon dioxide is being done in the Martian atmosphere as we speak. On board the Mars Perseverance rover, there's housed the MOXIE system, and there you can see on the right-hand side a depiction of the MOXIE system in its thermal insulation and cladding. And MOXIE is operational at this point. And on this contract, on this project that we are working on, the industry partner is Oxide Energy, which had a hand in doing most of the development of the MOXIE system in collaboration with NASA. So there is a solid oxide electrochemical cell in space on board the Mars rover. Now, we want to consider the possibility of tapping into bipropellants and using these in a solid oxide fuel cell for mobile applications. To this author's knowledge, there's been no in-depth study of such a system, with the exception of a NASA tech briefing that was released in 2010. But after this briefing, which is just a few paragraphs long, raising the possibility, we know of no further work that was done in this area. The primary and the first system that will be outlined within this project will be the development of a system that consumes hypergolic bipropellants. And these are in the form of hydrazine and mixed oxides of nitrogen, oftentimes stored in the form of nitrogen tetroxide. And you saw there in the animation, these are hypergolic because as soon as they touch, they ignite. They need no catalyst or anything like that. On its own, hydrazine is also a monopropellant, so it can be decomposed with a catalyst, and that is a strongly exothermic reaction as well. So we're going to take advantage of that within our system and bleed off some hydrazine, decompose it into a reformed fuel that we can flow into our fuel cell. Now, we've been talking about solid oxide fuel cells. We want to pause briefly and look at the operation and their working principle. As opposed to lower temperature fuel cells, solid oxide fuel cells, as their name suggests, use a solid oxide or ceramic membrane as the electrolyte. And through this membrane, oxide ions are conducted across. So oxygen comes in, it's reduced at the cathode, flows through the membrane, and then reacts with hydrogen on the other side to form water. The Nernst potential is the equilibrium voltage of a given reaction set within a fuel cell. In addition to this, a fuel cell, when it's actually operational, will have certain losses that come up in the form of the finite reaction kinetics. That's in the accounted for in the activation overpotential. You have the ohmic overpotential, which accounts for the resistivity through the conducting portions of the cell. And then you have a concentration overpotential as well, which is, again, due to the finite speed of gas diffusion through the electrodes to the reaction sites. And on the right-hand side, you see here an expanded view of the planar SOFC stack architecture, where you have bipolar plates that are interconnect plates that sandwich the anode, the electrolyte, and the cathode. And then they have these gas channels through which the reactant gas can flow, and the product gas can be exhausted. Now, there are certain developments that are necessary if SOFCs are going to be feasible for spacecraft application. We can see here on the right the working temperature range of the most common fuel cells. You have a PEM cell, you have alkaline fuel cell, the lowest temperature, you have a molten carbonate fuel cell, and then SOFC will typically operate, though it can operate sometimes down at 600 degrees C, oftentimes it will operate above that. There are trade-offs that are associated with this operation, with this operating temperature. On the one hand, you have high-grade waste heat that can be used you can hybridize an SOFC with another type of heat engine cycle oftentimes. You have rapid electrode kinetics, which again is why these fuel cells are resistant to poisoning oftentimes and are quite fuel flexible. The disadvantages of these types of fuel cells is that they have a slow startup time. This is limited by oftentimes the brittleness of the ceramic membranes and the risk of delamination between the layers. So each of the layers will have its own respective thermal expansion coefficient. And if startup is done too quickly, sometimes these layers can delaminate from each other. So certain developments are necessary, and these developments will be where our research focuses. So looking at the cell level, down at the level of the micron thick electrodes and electrolytes, the manufacturing and the enhancement of solid oxide fuel cells with high efficiency and power density is necessary if we're going to enable longer mission times, and we're going to increase the power density of these fuel cells so that they can better compete with the batteries. And we also need to think about the management that is inherent to the thermal expansion coefficient mismatch between the electrolyte and the electrode layers. So again, we want to lower the risk of delamination through thermal cycling. So these will be two objectives at the cell level. And then developments that are necessary at the system level is to create a system architecture and control operation which protects the SOFC. during mission transients. And we also want to be able to interface with existing aerospace components so that this fuel cell would be drop-in ready. Now, in thinking specifically about the electrode manufacture, this was the process throughout this project where theoretically we could tune the powders that are used to form the ceramic cell. We also do modeling of the electrode and its local microstructural properties, and fed these models into a genetic algorithm to optimize at the microstructure level the SOFC. And then again at the macro level, we want to perform evaluation of cell performance in a dynamic system model. So we're going to, throughout this research, we have developed the tools that are necessary in order to do this. The manufacturing method of choice as we collaborated with the Air Force Research Lab was an aerosol jet deposition machine. So aerosol jet printing enables a designer to control the deposition of active materials. Many of the process parameters that we used and tuned through our theory lead to the tuning of an ink formulation, a powder formulation by its composition, porosity, and a green body microstructure. With aerosol jet printing, we get really fine control over the layer thicknesses, the thickness of the electrolyte and the electrodes. It also introduces the ability through this 3D printing process to add compositional gradation, where we have a smooth gradation from one material to the next. And so you can, you're probably already thinking ahead, and you can see here the possibility of softening these interfaces between the respective parts of the SOFC. And on the manufacturing end, again, thermal processing profiles will affect the density and the porosity and the tortuosity of the final cell. The tortuosity is the effective path that is added as a result of the twisting, the turning that any kind of charge carrier or molecule must proceed through in contrast to the geometric dimensions. On the right-hand side there, you see a video of the aerosol jet deposition happening in printing coupon cells or button cells. Now we wanted to formulate a problem that could be solved readily so that its outputs, when they are fed to an optimization algorithm, don't take, on the order of days or weeks to solve. As some groups have done, they have reconstructed the electrode geometry at the pore scale, doing a full tomographic or three-dimensional reconstruction, and then simulated this through multiphysics and FEA. But those simulations take quite a while to run, and if we're going to sample through thousands of individuals based on a material set of interest, then we want to study this problem in a reduced order environment. Now, as I already discussed, if you look at the diagram up here on the right-hand side, this is a diagram of an electrochemical cell with an electrolyte in the middle and electrode on either side. And here you can see quite clearly the definition of what we'll call the overpotential, or this is the polarization resistance. And this is what I alluded to earlier, overpotential, which occurs as a result of the finite reaction kinetics, the finite rate of gas diffusion, and the conductivity of the charge carriers. So we formulate this problem. The overpotential is related to the difference between the Fermi level of the electrons and the ionic component of the potential within the electrode. So we define this differential equation here at the top, where the gradient of the overpotential is equal to the ionic component of the current density multiplied by the ionic component of the resistivity minus the electronic component of the current density multiplied by the electronic component of the resistivity. If we take the second derivative of this, assuming that we have a cell which changes its composition throughout its thickness, then we have this differential equation that is laid out here on the screen. This does correct some previous errors that exist within the literature. Some other groups have studied functionally graded electrodes, but oftentimes when they took this second derivative here, they failed to account for the fact that the resistivity and the porosity, therefore the diffusion, the gas diffusion, could change throughout the electrode. So this has to be approached as a coupled problem. Now, just briefly, if we do dimensional analysis on this, we find that we can reduce the problem down to the autonomous ODE on the bottom left-hand corner right here. So this hyperbolic sine function is, again, an autonomous ODE, so we don't have any analytical solutions to it. This is something that we're still working on, and I'll review this in some of our future work at the end of these slides. But we are still trying to find some analytical solutions to this, to the Butler-Volmer overpotential in limiting scenarios. What's important for us to just notice briefly here is that this term here is essentially the ohmic resistivity divided by the activation resistivity. And a couple of authors have denoted this as the electrochemical Thiel modulus, which the Thiel modulus is a modulus that is oftentimes used in catalysis to measure how effective a catalyst, a reactor, is. And what we'll find throughout this optimization is that, generally speaking, SOFCs are poor catalytic reactors. They're poor, they do a poor job at being catalytic reactors. But they do a better job at being conductors, we might say. So throughout our numerical optimization, we saw this trend over and over again, that the best performing cells were not necessarily very effective. The overpotential was not well distributed across the electrode thickness. It was mostly concentrated at the surface, at the interface between the electrode and the electrolyte. Now, looking at some of the inputs that we need for our problem, and here I'll just again point out, we have to define this ionic and electronic resistivity. We have to define the area of the triple phase boundary, which is the boundary at which the oxygen and the hydrogen can combine and then desorb in the form of water. And we have to also define our exchange current density, which is the J naught term. As we think about this, we think about forming a porous conductor that is formed of various grain sizes. The first thing that we did was we verified the particle size distributions of our ink through wetted laser diffraction here at Tennessee Tech. And here you see a schematic of a typical SOFC. The cathode will be formed of a LSCF, which is a lanthanum with a strontium doping and cobalt ferrite material. You also have a samarium doped ceria, a yttria stabilized zirconia electrolyte, and a nickel oxide YSZ interlayer. And then upon operation, this nickel oxide will be reduced to nickel. So here we have the particle size distributions for these various powders, and we can see here, noticing that the x-axis is a logarithmic scale, that these are all can be assumed to be log normal distributions. Some of them show some bimodality, but overall they are log normal in their distribution. As well, once we print a cell, then we can image it using scanning electron microscopy, and then process those images. What you see here on the left-hand side is an overlay of an SEM image and an EDX image, energy dispersive spectroscopy, which looks for certain atomic spectra. So here we have an overlay showing us exactly where the YSZ is in yellow and where the nickel is in the kind of bluish purple. After this, we pull out the porosity. We threshold the porosity locally, and then we use a randomized line intercept method to discern, again, the particle size distributions after after the cells have been sintered and prepared for operation. Noticing here again, quickly in the image on the left-hand side, going forward within our analysis, we're going to assume that all of the grains have approximately a spherical structure to them, which does well. But the theory that we'll lay out is not necessarily unique to spherical distributions. It can also be applied to other morphology particles as well. Now, in thinking about the theory of conductors, we want to broach the topic of percolation theory. And you can see here in the diagram in the upper left, a schematic showing the ability of certain charge carriers to conduct all the way through from the electrode interconnect to the dense electrolyte. And this only happens if a phase is at a certain threshold and of a certain type particle size. So the percolation refers to the phase's ability to form an unbroken chain from one conductor to the other. So a single particle size coordination, this is for monodispersed spherical grains, is given by this relation. The coordination number just refers to the number of particles that a given particle is in contact with, which will tell us whether or not it's able to form a conductive path. Now, Zhang in Journal of Power Sources laid out this generic integral formulation here for particle size for coordination numbers with a probability size distribution to the grains. We also, again, notice that Lin showed in 2018 that particle morphology has a smaller effect on the percolation threshold than the size distribution. So particle morphology can refer to grains that are more of a cuboid or a tetrahedron or something like that, as opposed to a sphere. But many of these percolation thresholds are going to be, the patterns and the functions are going to be somewhat similar. Now, again, we are assuming here a log normal distribution. This helps us because the solution to this integral formulation is not analytic if we have, say, a Gaussian distribution of grain sizes. If we have a log normal distribution, we can find an analytic solution. That was not found in the previous publication. This is a novel solution that we have formed here. This is the analytic integral for spherical particles with a log normal distribution. So this defines their coordination number, basically the ability of a particle of one phase to contact a particle of another phase or another particle within its own phase type. See here the maps and the trends for the coordination number and the percolation probability as a function of the polydispersity of the grains. And so you can see here that for phase one to be able to contact and percolate, form a percolating network with phase two, that decreases as you decrease the standard deviation of phase one and increase the standard deviation of phase two. So you end up having particles of one phase that end up blocking out the particle of the opposite phase. Now, where this is important, again, the percolation probabilities define the critical composition and size distribution at which conduction can take place. Now, previously in the literature, as we move forward in applying this to the properties that are relevant for the electrochemistry, the length of the triple phase boundary, and again on the right-hand side you see here a schematic of the triple phase boundary, using relations from stochastic geometry in previous papers. Gokel in 2009 defined a relationship of the length of the triple phase boundary normalized with respect to volume as a function of the coefficient of variance and the skewness of the particle size distribution, as well as beta, the shape factor of the phase particles or grains. So there you have the definition of the length of the triple phase boundary locally within the electrode as well. And in 2019, the surface area of one phase with respect that is exposed to the pore space was also defined in terms of a stochastic geometry. Adding our percolation theory here, we arrive at this equation here, which defines locally the area of the triple phase boundary. And you can see here that the triple phase boundary, the density increases if the particle sizes are monodisperse. So the more we shrink down the standard deviation of the particle sizes, the more evenly distributed those particle sizes are, the better triple phase boundary we get, the higher density we get. Here you see on the right-hand side diagram of where the average particle diameter or particle radius of phase one is twice that of phase two, and so you get this shifting in the map. Now, the triple phase boundary is also dependent not just on the standard deviation, but also on the mean. You can see the critical nature here of this percolation threshold. So looking at the triple phase boundary density map on the left-hand side, there are areas where if the mean of phase one and phase two, this could be nickel, YSZ, or you could think about particles on the cathode as well, where if those means are too disparate, then you're not going to get an effective percolating triple phase boundary. As well, on the right-hand side, this map is perhaps interesting to look at if we had an electrode or a microstructure composed of many different, of multiple phases, 3 or 4 phases. For a biphase material, obviously the only compositions that are possible are just going to be a plane that is cut across from 100% phase 1 to 100% phase 2. So we would take a cross section of this mapping here. But this shows how tuning the initial inks and powders can also increase our electrochemical activity. What we have done is moving beyond this and thinking about conductors or electrodes where it's necessary to know how much surface area of one phase is exposed to itself, we might say. We have defined these relations here for the surface area between the surface area of contact between particles of the same type. So this would be nickel on nickel, YSZ, YSZ, LSCF with LSCF. In addition to that, we have also defined a novel relation here for the interfacial surface area between particles of two separate phases. Again, using here notions of stochastic geometry and deriving some of these relations from algebraic topology, where we can see that the dihedral angle, the length of contact between grains, is related to our triple phase boundary definition as well. Now, where all of this is important is in defining grain boundary, effective geometric grain boundary conductivity and the overall conductivity of the electrode. Now, we localize the conductivity using a particle layer model. Then the geometric surface area and the geometric length of the electrode are shrunk down to characteristic surface areas and characteristic length scales. The tau here is the tortuosity of the cell. And if empirically someone has defined a grain boundary conductivity of, say, YSZ, which is also oftentimes different than the bulk value, then the geometric addition to that effective conductivity is here given by this expression here, where S sub ij is again given by this expression that we already showed before. And then the bulk conductivity and grain boundary conductivity can be defined through the equation on the bottom. Now, we want to compare our model and our assumption of spherical packings and percolated spherical microstructures to images that we have. So we did a comparison of our stochastic geometric approximation, compared that to SEM images that we processed in MATLAB, and again measured the porosity across the slices, used the randomized line intercept method to discern the particle size distribution. And we find, here's a sample of an anode. In white, you have areas of, you have the triple lines between the grains. This is where electrochemical reactions can take place. And using our model, it correlates well with the values computed directly from SEM. So here we have the triple phase boundary density, and we have the grain boundary interfacial surface area density as well. Now, moving on, we think about the gas transfer that happens within the electrode. The most accurate diffusion model for multi-component gas diffusion is the dusty gas diffusion model, where the solid phase is also considered to be essentially a gas species. And you have what's called Knudsen diffusion, which is defined by the average mean free path of a particle given at a certain temperature. And it will also be a function of the local pore size as well. So this becomes relevant, especially for hydrogen on the anode. Now, previous papers have used Graham's law, which just says that the cross diffusion of species is going to be related to the ratio between their molar fluxes and their molecular weights. And that would be true if we were just looking at just a porous geometry. However, this is not true under the case of chemical reactions. We cannot use this equation anymore to simplify the dusty gas model. Instead, what we have done is impose this constraint that the local flux, and here I've just defined the local flux of hydrogen, is going to be equal to my local current density divided by 2 multiplied by Faraday's number, and then multiplied by the local area of the triple phase boundary. And doing this, and we will have the, you can be referred to the full derivation of this within the dissertation text. But we have defined this novel Laplacian of gas diffusion under electrochemical reaction. And this is in the case of isobaric diffusion in anisotropic media. So this Knudsen diffusion term here and here can again change because my porosity can change throughout the thickness of the electrode. Doing all this, we finally form a boundary value problem, and this defines the electrochemistry for the electrode. Here we just have at the top the expression for the overpotential. We have the expression for the electronic current density, the ionic current density, and then here defined the gas diffusion for an anode with a hydrogen nitrogen steam mixture here. And you see the two expressions for the electrochemically active species and the inert species in the nitrogen, how those expressions change. As I mentioned, besides enhancing the electrochemical performance of a cell, we also want to change the interfaces between the layers. And so we need to take into consideration in our optimization the thermal stresses that are present in a mixture of two materials, and what thermal stresses will be created in a graded electrode. And so here we have just the relations, the effective Poisson's ratio, the thermal expansion coefficient, the Young's modulus, the bulk modulus, and the rigidity modulus for a mixture of two materials. And here I just want to show a sample of doing some of this analysis for a functionally graded nickel and YSZ electrode. So if we use the 3D printing process and we print using these concave down profiles of varying degree up to a linear profile, you can see here on the bottom kind of a graphic representation of that microstructure. The thermal stresses that result are shown in the right-hand graph. Positive stresses are tensile and negative are compressive. So we get a bending moment as a nickel-rich surface has a higher thermal expansion coefficient than the YSZ. It's again trying to delaminate, pull itself off of the electrode. Same type profiles are shown for concave up. Now, these result in the minimal absolute thermal stresses down to the minimal tensile stresses. So these concave up profiles will be preferred, and it also happens that these concave up profiles are preferable for the electrochemical performance as well. Well, now what we did is we fed this boundary value problem with the electrochemistry and the thermal stresses into a genetic algorithm. And here we see the benefit of using a reduced order model such as this is that we can sort through thousands of individuals in less than a day. So someone can have a material combination that they are interested in for an electrode, and within a day or two, they can have a relevant answer of what the ideal compositional 3D printing profile would be for that electrode. Here we see the individual that performs the best as far as reducing the absolute thermal stress is individual A with a linear gradation. Individual B has the minimal polarization resistance. Now, interestingly, let's look at just in brief detail at individual B here. You remember I introduced that idea of the teal modulus. Here you can see that the polarization resistance, the overpotential, is not evenly distributed across the cell. There is no boundary condition here that says that the overpotential has to be 0 at the current collector. But the optimal performance electrode, or the optimal performance anode, does concentrate this overpotential at the electrolyte interface. Again, showing that electrodes are ineffective catalysts, but they're good conductors, we might say. And we're continuing to try and find ways of making the electrode more effective, as in distributing the overpotential throughout the thickness, while also maintaining the minimum polarization resistance. Interestingly enough, here individual C, lying on the shoulder of the Pareto front, is just a homogeneous cell. And we find that it has virtually negligible tensile stresses, but an extremely high compressive stress right here at the interface with the electrolyte. So there would be risk that would be associated with this, but we find that the particle sizes that we have currently been working with, sometimes a homogeneous cell can perform nearly as well as the compositionally graded cell. Now, changing up our materials, that was for a nickel YSZ electrode. We also looked at a nickel MgO with basically a nickel manganite and a samarium doped ceria anode, and again fed this into the genetic algorithm and sorting through 24,000 individuals in the parameter space and imposing a current density of 1,000 milliamps per centimeter squared, and then optimizing to that. We find here that this individual satisfies both the criterion of minimizing the thermal stresses and also minimizing the polarization resistance as well. This study developed a very sharp Pareto front because this individual and many other brothers and sisters that had virtually the same properties were all found to result by the final generation. As well, we also wanted to look at cathodes, and here the cathodes are unique because oftentimes they incorporate a mixed conductor, a mixed ionic and electronic conductor. So the LSCF serves both roles. This was an opportunity for us to use and implement some of these stochastic geometric relations that we already derived for the grain boundary effective conductivity and the percolation between phases. So here ions can conduct through the LSCF, then through the SDC to the electrolyte interface. And we found this to be an optimal profile, again, in minimizing thermal stresses. These are two ceramics that are mixed together, so the thermal stresses are reduced. But this profile also reduces the overpotential as well. You can see here is the overpotential, the profile changes rapidly as that SDC approaches its percolation threshold, or its critical composition. Now, we also found through our optimization that given the preference of porosity gradation versus compositional gradation, in a conductor that has two phases with fairly disparate conductivity. So in a nickel YSZ anode, the nickel electronic conductivity is about 6 orders of magnitude higher than the ionic conductivity of the YSZ. In these type of scenarios, porosity gradation was actually preferred. And so we have printed a porosity graded cell and verified the porosity gradation through SEM and compared its electrochemical performance to previous prints. And we find that we get a 32% increase in the power density in a porosity graded anode. Now we're still doing more studies on the compositionally graded cathodes and other types of other materials for the anode as well. So we hope to get further verification and feedback to critique and correct our model. Now, again, as I already said, we want to enhance the electrochemical performance of the cell, and we want to manage that thermal expansion coefficient mismatch between the SOFC layers. The research laid out thus far goes over my assistance in the development of the SOFC at the cell level. We also did some studies at the system level, and again, to assist those developments which are necessary in order to make this a feasible spacecraft system. This is our proposed hypergolic bipropellant-enabled solid oxide fuel cell system. This utilizes proven technologies in monopropellant catalyst beds, recirculation ejectors, and propellant tanks that are already being used. Another side benefit to such a system like this is that we can exhaust the SOFC gases and perhaps run them through cold gas thrusters to get additional thrust work from the bipropellant products. So here the working principle is that we would have a helium secondary pressurant, which pressurizes a hydrazine and a nitrogen tetroxide tank. The hydrazine flows through a catalyst bed, and here I've separated, just for the diagram, the heat exchanger. But we've looked at a design that would effectively utilize a two-chamber heat exchanger, where the reacting and decomposing hydrazine is flowing counter to the nitrogen tetroxide, bringing the oxidizer's temperature up and helping it decompose, so that by the time we have the gases entering the SOFC, all the gases are those which can be suitably used by the system. Now, first we did some steady state analysis on a system like this in engineering equation solver, and estimated that for an 18-day mission with a continuous 1 kilowatt load, no recharging available, the fuel cell plus the fuel and the oxidizer, as well as the radiator that was included here to radiate excess heat, came out at 286 kilograms for an 18-day mission. Primary batteries to do the exact same mission was 808 kilograms, and secondary batteries, or rechargeable batteries, were 2,700 kilograms. Moving on from the steady state analysis at ease, we also developed a Simulink model of an atmosphere independent SOFC. This involved creating a dynamic model of the fuel tank for the hydrazine and the nitrogen tetroxide. And for each of those, we also created our own equations of state using existing testing data from Aerojet Rocketdyne from reports that they had published back in the 60s. We also developed a dynamic model, the two-phase monopropellant catalyst bed, and developed a dynamic model of the planar SOFC. Especially as we're running short on time at this point, I'm not going to go into all the details of this model, but we have included methods by which we account for the effective viscosity, the effective thermal conductivity of gas mixtures of up to 10 species at a time. We also take into account here the temperature, the thermophysical properties that are temperature variant as well. Just a quick outline here of the decomposition of gases that are flowing into the SOFC anode. Here you see in the catalyst bed, the hydrazine rapidly decomposing. Here we've modeled this as a nickel iridium catalyst. The hydrazine decomposes and begins to form both ammonia and hydrogen and nitrogen. And so by the exit here, we've tuned the particle size and the heat input. This is a continuous 20-watt heater. By the time we exit the catalyst bed and the gases would be entering the anode, we have even very little ammonia left. But we have done studies on ammonia as well, ammonia in the cathode, or ammonia in the anode, excuse me. One thing that we also added in the simulate model, because most SOFC stacks use a cross-flow pattern. I'm going to hope that my video doesn't crash here. Sometimes it crashes at this point. Most of them utilize a cross-flow pattern where the anode and the cathode gases are flowing orthogonal to one another. Because of this, the symmetry of the problem is broken and can't be reduced to one dimension like a counterflow or a co-flow case. So we created a plugin, basically, or a function for Simulink, where we wrote our own variable time stepping implicit heat transfer solver, finite difference solver. And we embedded this, wrote it in C code, and then have embedded it in Simulink via an S function. And by doing this, even during temperature ramp up and ramp down, the model is the finite difference solver is still able to run 5 times faster than real time. Now we see here some of the transient profiles for a system warm up and start for the hypergolic bipropellant system. Here again, we see this is a 30-minute warm up, a 30-minute startup, excuse me, and an initial period to equilibrate the cell. We ramp up here to a little over 1 kilowatt. The stack size of choice throughout the project was a target of 1 kilowatt, and we are able to do that. We've done some control optimization as well in manipulating the recirculation gas valves. The temperature profile here on the bottom, that is done at 80% exhaust recirculation rate, and we find that this is possible with the ejector pump. And by doing this, we can minimize the temperature difference across the cell, basically the maximum temperature minus the minimum temperature. We also shrink down the delta between temperatures at a given node, and these nodes are taken crosswise across the stack face. And then we also reduce the differential between the anode and the cathode exit gases or exhaust gases. Overall system behavior is highly dependent on the recirculation rates, both for the anode and for the cathode. We can also reduce the temperature difference across the cell through fuel utilization, but as we see here, it's less sensitive to fuel utilization changes than it is to recirculation of the exhaust. At different fuel utilizations, we back out a power per propellant flow rate, basically watts per kilogram per second or joules per kilogram from our propellant. We find here in the bottom that our power output does decrease, obviously, with system recirculation, but our efficiency will increase. We also have the propellant-specific energy for varying fuel utilizations here, and this is at 80% recirculation. We find that we get a system that has about at 80% fuel utilization, the specific energy is about 0.9 kilowatt hours per kilogram. We can readily compare this to the theoretical value of the hydrazine NTO pairing, which is about 1.6 kilowatt hours per kilogram. By doing this, by looking at a total system and its associated weight, and it's the power density of a stack and the effective energy density of the fuel given the efficiency of the stack, we can calculate the power density and the energy density as a function of the mission duration for the spacecraft. You see here the functions on the left-hand side. These the power density, the effective power density of the bipropellant is going to again be that watt-hour per kilogram figure divided by the mission duration in hours or whatever the increment might be. When we graph the energy densities and the power densities together, we have these Rigoni plots. A Rigoni plot compares the energy density and power density of a system. And we find that for the hypergolic bipropellant-enabled system, we have at 30 minutes of continuous operation, we've pretty much reached our break-even point where we are now beating the performance of the batteries. And these are here laid out the current battery technologies that are oftentimes used. So at 30 minutes, we're beating the battery. Where the liquid, the hypergolic bipropellants really come out on top is when we look at the volumetric Rigoni plot, where we see that the energy density in terms of watt hours per liter outclasses the battery technologies. And even if we were to map state-of-the-art or even battery technologies maybe 5 years down the road, this type system with the liquid propellants would still come out ahead. Now, doing the same type analysis, once we had developed the Simulink models, we could analyze similar systems as well. And if we look at a proposed regenerative solid oxide electrochemical system as well, think about its benefits. The ability to switch, the ability for a galvanic cell or a fuel cell to switch modes into electrolytic operation is advantageous, where you might have an application where a rechargeable battery is useful, but maybe you want to get a little bit higher energy density. Previously, some hopeful applications for regenerative fuel cells of all variations of low temperature fuel cells up to high temperature fuel cells has been laid out before in the literature. And we find that for a low Earth orbit satellite, the battery is favorable. For a geosynchronous orbit, it has an eclipse time of about an hour and a half. A regenerative fuel cell could be beneficial. So again, we've developed a Simulink model here for the regenerative system and done pretty much the same analysis that we did for the hypergolic system. And we find here the maps of the power density and the specific power density and the volumetric power density and the specific energy density and volumetric energy density as a function of mission time for a hydrogen-oxygen regenerative fuel cell. Again, plotting out the same type Rigoni plots. We find here that, again, in terms of the specific energy density and the specific power density, this type of regenerative SOFC, SOEC can benefit in an application that is mass constrained. And here, notice again the logarithmic plot on the x-axis. However, in a volumetrically constrained system, the hydrogen-oxygen regenerative cell does not come out ahead of most current battery technologies. Now, the pressure of the gases in this study was about 20 bar for the hydrogen and the oxygen. If developments were made where the hydrogen and oxygen could be stored at much higher pressures, at hundreds of bar, and the appropriate downregulation of the pressure, the gases before they enter the solid oxide electrochemical cell, if that could be done, then perhaps once again the regenerative cells might compete with the battery technologies here. But these kind of preliminary studies are useful to do before the technology is pursued in greater detail or more earnestly. And the final system that we want to lay out here, and this is a proposed future system that again would utilize solid oxide electrochemical cells, would be a heat engine operation. So the working principle behind this is you have a solid oxide electrolytic cell, which is sitting at a high temperature, which is receiving heat from some type of high quality heat source, be it a nuclear reactor or a radioisotope source. And then you have an SOFC at the lower end of a temperature gradient on the system. And just by flowing gases around in a closed loop, you can get out net work from the system. To see how this is possible, you notice here the temperature-dependent plot of the Nernst potentials. The Nernst potential is, again, a function of the Gibbs free energy of the reaction. And for the hydrogen, water redox cycle, you do have this temperature dependence here, where if you operate the electrolytic cell, maybe up here at 1200, 1300 degrees Kelvin, the electrolysis is facile compared to the fuel cell operation, which is actually going to give you a higher voltage or a higher potential. So it's the net potential difference between these two coupled cells that are running in a constant current loop that it's through this type of operation that you can get net work out. Now, this type of system we haven't studied in a transient scenario, but you could again imagine a scenario where you flow in fresh products, and then you bleed off excess reactant for use maybe at a different time, so that you do have this, you've built in this load following capability to a heat engine. And normally the heat engine, be it the solid state thermoelectrics, they are just steady state operation, no load following available unless you have like battery storage or something. But here we're able to do this we're able to perhaps store energy in a chemical form and while maintaining a closed loop if we want for just electrical power output. Now, our choice, our proposed system, utilizes carbon monoxide and carbon dioxide, because as you can see here, the Gibbs free energy of reaction is more temperature dependent for this redox cycle than it is for the hydrogen steam cycle. And so we have done some steady state analysis on this as well. building a Simulink model to mimic this type of system. And what we find is that for low current densities, we can get power output with a thermodynamic efficiency of up to 30%, a total thermodynamic efficiency of 30%. This is not the Carnot efficiency. This is the thermodynamic efficiency. Even here at the maximum power point, if we ramp up the current density, we can get a power density that is about 1.42 milliwatts per centimeter squared. Even at this maximum power point, we have an efficiency of about 13.7%, which doubles the efficiency of current solid-state thermoelectric devices that have efficiencies on the order of 3 to 6% oftentimes. Now, further analysis needs to be done in the packaging of this system and how the power densities would compare to, say, the power densities of solid-state thermoelectrics. But at least the system as envisioned here seems promising. Now, our conclusions. The conclusions at the cell level, again, as we saw, it is possible to significantly enhance the SOFC performance by tuning the microstructural parameters of the SOFC. It is also possible, depending on the material selection, to enhance the electrochemical performance through compositional and porosity gradations that are implemented through the 3D printing method. It is also possible to utilize functional grading to manage the thermal expansion coefficient mismatch between discrete cell layers. Now, our conclusions at the system level, in looking at and thinking about the hypergolic system that we first proposed, it is possible to warm up, operate an SOFC assisted by the exothermic decomposition of hypergolic bipropellants. And it can be advantageous from the standpoint of gravimetric efficiency, but especially volumetric efficiency to utilize liquid bipropellants for long duration missions. For the regenerative cell, it can be advantageous from the standpoint of gravimetric efficiency, but not right now from the standpoint of volumetric efficiency. Now, further developments in, as I already alluded to, in storage pressure of the hydrogen and the oxygen can increase volumetric efficiency. And I realize I put liquid hydrogen and liquid oxygen here, but after they run through the SOFC and they come back, we're assuming that they're in gaseous form. We don't have a condenser or anything like that. And then thirdly, here at the system level, the electrochemical heat engine poses promise as a means of developing electrical power from a high quality heat source with few moving parts, just one pump. And we leave open the possibility of hybridizing that kind of heat engine with another type of heat engine cycle, one with moving parts like a Brayton cycle, or we can have a bottoming cycle from a solid state thermoelectric that operates from the temperature at which the low temperature SOFC is operating and radiating heat out to outer space, basically, and that will depend on the location of the vehicle within the solar system as for what that background temperature is going to be. Future work at the cell level, again, continued testing of printing structures will validate and correct the theories that we have laid out. And novel microstructural geometries that increase the reaction surface area or grain boundary interfacial surface area should be explored and can be explored with very little modification to our theory. So this could involve columnar grains that have a very high grain boundary conductivity in the case of like an LSM cathode, Our stochastic geometric relations would apply to those as well. Someone would only need to substitute the shape factors for those grains and their respective percolation probabilities. At the system level, in further analysis as far as the material compatibility with these hypergolic bipropellants will elucidate future safety factor issues. And we would like to add to the system modeling perhaps a means by which we can estimate thermal stresses real time, again, implementing a finite difference scheme and using the inputs from the thermal finite difference scheme that I laid out earlier. And we also would like to study the effects of functional grading on the heat generation and thermal stresses during a startup procedure. Future work, since we're pretty much out of time, I'm not going to really go over this, but we are doing some dimensional analysis of these electrodes and hope to publish some of this work in an upcoming paper in the Journal of Physics. Again, looking at the ratio between the ohmic resistivity and the activation resistivity, and seeing if through functional grading we can have cells that perform well from electrochemical standpoint, but are also more effective catalysts. We utilize more of the thickness of the electrode. We have also found an analytic solution for the Butler-Volmer, or excuse me, we found an analytic solution for the electrode problem at the TOEFL limit, or at higher overpotentials. We've also created a multi-physics model in ANSYS, I wasn't quite satisfied with the results that we were getting from this, and so further work needs to be done on this model as well. Finally, I want to thank our funding sources. This work was funded by the Air Force Research Lab through a subcontract managed by the Defense Associated Graduate Student Innovators, DAGSI, and the SOCHI program. And I want to thank our team members that we've collaborated with on this AFRL SDCP project, the Seedlings for Disruptive Capabilities. We've interacted with Kirtland Air Force Base with the AFRL Space Vehicles Directorate. We've also been collaborating with Wright-Patterson Air Force Base, the Aerospace Systems Directorate, and the Materials and Manufacturing Directorate, as well as Sandia National Lab, University of New Mexico, University of Dayton, and Edwards Air Force Base has been doing some of the materials compatibility testing. And finally, Oxide Energy has been a great source of help on this project, and they're the ones that are actually manufacturing the cells and the stacks. So with that, I want to again thank you all for your attention. I know we've gone way over time here, but I want to open up the floor for question and answer.